from Imperial College London. I'm the session chair for the session on databases and emerging hardware. So we have 6 presentations in this session. So the first one will be given by Alexander van Renen. He's a PhD student at TU Munich, and he'll be talking about databases and non-volatile memory.
Okay, thank you for the introduction. So as you heard, my name is Alexander van Renen. I'm a PhD student at TU Munich, and we at TU Munich look at non-volatile memory and try to figure out how we can integrate this into a database system. So this work was joint research with Fujitsu Labs, and I would like to thank them very much for their continuous support and help. Okay, so if we think about non-volatile memory, we first have to look at what it actually is and what it can offer us. So we have the normal memory hierarchy here, and on the very top we have DRAM. DRAM has very low access latencies, and so we can store and retrieve data very fast from there. And it offers us this cache line-grained interface, so we can load individual cache lines from memory into our CPU. But on the downside, the price for DRAM is rather high. So in addition, the capacity is limited, so we can not fit an infinite amount of memory into one system. Therefore, we also have storage devices. These have different technologies, so we have these SSD Optanes from Intel, which already use non-volatile memory. However, they are still attached with a PCI Express bus. So the access granularity is on a page-grained level. So we access 4 kilobyte, for example, instead of individual cache lines. And the reason for that is due to the PCI Express bus, the access latency is really high. We see 18 microseconds here. But the advantage of these technologies is that we can store a lot of data on it very cheaply. And here comes in this cost argument David Lomé made in his talk at Damon on Monday. We have different data in our database system. We have hot data, we have cold data, and we want to store the cold data cheaply and only the hot data on the expensive memory devices. So we should keep this in mind. But now you've probably noticed there's an empty row, and I'm talking about non-volatile memory. So enter non-volatile memory. Non-volatile memory has been constantly announced by Intel over the previous years, but we're expecting it to finally arrive to the market within a year. So what is non-volatile memory? Non-volatile memory is kind of this in-between technology. It bridges this gap between DRAM and SSDs. And we can see the access latency is similar to that of DRAM. We have also this byte-grained access pattern, and we have a price and a capacity which should also be between DRAM and SSDs. So this gives way for a lot new design spaces. And in case of that was not clear, non-volatile memory is actually persistent memory. So if you store something on it and the power goes down, it will still be there. Okay. So now, as database people, we have to ask ourselves, how can we best make use of this exciting new technology? And this will be basically the main content of my talk. For this, we will first look into existing approaches to the problem, and then we will show our own approach. Okay, so for the existing approaches, we have categorized this into 2 categories. The first one are NVM direct approaches, or at least that's how we call them. The idea here is that you build a database or a storage engine and you store the data directly on non-volatile memory. Meaning, in a database, you usually have a B tree or something like that. You put this directly on non-volatile memory and you also work there. This initially sounds like a great idea and has been a programmer's dream forever, that you can just work on your data structure and it's immediately persistent. But, however, it doesn't work that easily because what we call failure atomicity. So imagine you have your B tree and you do an insert. During this insert, you move from one consistent state where the tuple is not already inserted to another consistent state where you have the tuple. But in between, there are some in-between steps, right? For example, you might have a node split. And these in-between steps are kind of a problem because imagine your system crashes at this point and it's on non-volatile memory. When you bring it back up, you will have the same inconsistent state. And you need a way to either avoid these or to be able to recover from these. So this is a huge challenge for programming, and we've seen a lot of work in this area trying to solve this problem, also in an efficient way. But it's not easy. And there are some other problems with this approach. mainly the high non-volatile memory latency. So we have seen non-volatile memory is a lot slower to access compared to DRAM. So if we access a tuple, we immediately take a performance hit. In addition, this approach here is not really cost efficient because we're not using the DRAM and we're not using SSDs. So we're not optimally using our system resources. So if we go on, we can look at buffered approaches. In buffered approaches, we don't change data directly on non-volatile memory, but we rather have a buffer in DRAM. So you can imagine the system to be a simple buffer managed system where you just exchange the SSD or the hard drive, as in traditional systems, with non-volatile memory. And what you get here is you avoid kind of this problem with failure atomicity. You also use your DRAM. So you have fast access to the data which is stored in DRAM, meaning you can process the data really fast as long as you fit in DRAM. However, I would argue that we still not make optimal use of this new technology of non-volatile memory because we're not using the SSD. Okay, that's not. But we are not using the byte addressability of non-volatile memory because we are always transferring entire pages between non-volatile memory and DRAM. And the second disadvantage of this approach, it's not using the SSD. So we will build on this approach, but first let's look at how these different systems or how we would expect these different systems to perform. And these are not measured numbers, but it's kind of what we think they would do. So on the top here, we have the main memory database system. This one runs really fast, but it only can run in DRAM. So as soon as our data size, which we show on the horizontal axis here, reaches or goes beyond the capacity of DRAM, the system cannot work anymore. Then we have, with a similar kind of behavior, we have these NVM direct systems. So these have the same problem as soon as our data size hits the size of non-volatile memory. They can't run anymore. We're done. And what you also see, there's no difference whether the data fits into DRAM or in non-volatile memory, because these systems don't really make a good use of DRAM. So now let's look at the third approach we had, or the second approach, these NVM-based buffer managers. So we have a buffer manager between DRAM and non-volatile memory. And what these do, or what we suspect them to do, is they run reasonably fast as long as we're in DRAM, but once we hit non-volatile memory, their performance drops. And it drops quite a bit and drops beneath the performance of these NVM direct systems. Why is that? In the non-volatile memory direct system, if you access a single tuple, you simply go to non-volatile memory and load this tuple. So you loaded this one cache line. However, in the NVM buffer manager case, you would load an entire page. So this is what, 16 kilobyte. So you take a huge performance hit, and we estimate this here. Okay, then on the next slide, this is kind of our dream slide here. This is what we imagine that people would want. We want a system that kind of smoothly scales across the entire memory hierarchy. So for the case when we are in DRAM, we are similarly fast to DRAM systems. When we are on non-volatile memory, we can still leverage this DRAM buffer to outperform these systems that only use non-volatile memory. But still, we can also use SSDs and kind of scale to even larger data sets. So that is our goal. And in the second part of this presentation, I will kind of try to show how we can not really reach it exactly, but how we can get close to it. And for that, we need a few techniques we've come up with. So the first one we call cache line grained loading. This solves the problem, which I've already mentioned, that when we access a single tuple, we have to transfer an entire page in a buffer managed system instead of only the tuple. So we get around this in the following way. We simply transfer individual cache lines, and on the page, we remember which cache lines we've already loaded. This way, we can really improve the required memory we transfer between DRAM and CPU. So how is this implemented? I have an example here. On the left side of the slide, I show the page how it is in non-volatile memory. And on the right side, I show the page in DRAM. So say we have a transaction coming in requesting a new page. The page is allocated, but we don't load any of the data yet. We will load the data lazily when it is requested. So, for example, if a transaction were to access Tokyo, we would load this Tokyo cache line into DRAM, and we would set the flag in this resident bit mask here, indicating that we've loaded the first cache line. If we go on with that, we could load another tuple, for example, Redwood City, and we also set another bit in our residency cache line, in our residency mask. This way, we won't have to load the tuple again. And if we change a tuple, we do a similar trick by using a dirty bit mask, indicating which cache lines are dirty and need to be flushed back out. Okay, so with this technique, we can, as it says down here, reduce the amount of data we have to load and thereby significantly increase the performance and kind of get to a similar state where these NVM direct systems are. We simply load the cache lines we actually need and not a lot more. However, there's still kind of a problem which is a little bit hidden here, but you can see it by looking at this number. So any of these pages is in our system 16 kilobyte, so we have 256 cache lines. So in the example here where we only load 2 cache lines, we actually wasted the majority of the cache lines. So we waste a lot of precious DRAM, and we want to be cost efficient, right? So what we do is we introduce another concept we call mini pages. So this is basically a different page size now, and we kind of compress the memory here. Not with a compression technique, but by simply allowing only, in our case, 16 cache lines to be stored on this page. And to maintain this, we use a simple indirection mask. So this is shown here on the top. We use the slots array, and the slots array indicates for each of the slots in our mini page which cache line is actually loaded here. So the first slot here contains the Tokyo cache line. This comes from cache line 0, so we have a 0 in our slots array. The second cache line has changed to Munich, but it comes from cache line number 3, so we have A2, because it's 0 based, obviously. So this way, we can dramatically decrease the size of the pages and therefore use the available DRAM capacity a lot more efficiently. Okay, so using these two techniques, we basically move to a point where we are very similar and better than these NVM direct systems. So we kind of solved this middle part of our dream chart. However, we introduced buffer management, right? So all the stuff works with a buffer manager. And this gives us a problem. As we all know, buffer managers are kind of known to be slow. However, we can speed them up quite a bit by using a technique called pointer swizzling. We didn't invent this. This is common knowledge, or at least it has been used quite a while. But I will briefly go over how it works. So whenever in a buffer managed system we have to access a page, we have a page identifier, we have to go to a page table, looks this up, and retrieves the actual page. Now, with pointer swizzling, what we can do is we take this page ID, we use the first bit of the page ID, which we use as a bit flag to indicate whether the remaining bits are actually a page ID or whether they are in fact a pointer. In case they are a pointer, we can avoid this lookup in the hash table and directly go to the page we are referencing. So this is here with the blue arrow. So this is the idea of the technique. And now let's summarize this and look at what all of these techniques give us. So on this chart, from left to right, we subsequently add these techniques to a simple, basic non-volatile memory buffer manager. So this you can imagine as a buffer manager which just works with NVM instead of SSD. So it doesn't use any of these new features we have. And as we see, by adding cache line grant loading, mini pages, and pointer swizzling, we can get to a point where we outperform the NVM direct system. So now we kind of solved in our dream chart the first two sections. With pointer swizzling, we get kind of competitive with in-memory systems. With cache line grant loading and mini pages, we get competitive with non-volatile memory direct systems. And we still have to add SSDs to the whole thing. Okay. Adding SSDs is actually, as it turns out, rather simple in our system. This kind of shows how it is done. And I think the main insight here is that by having this division of memory into pages already, it's actually easy to add a third layer to it. The one interesting or the one important aspect here is we want to add the SSD in a way that it doesn't impact the performance of our engine as long as the data still fits into either DRAM or non-volatile memory. So we want basically to have the SSD for free and only use it and only pay for it once we have to spill to SSD. Okay, and how we do this or how this is done is in a way that we use one page table for both pages in DRAM and in NVM. What this gives us, instead of using 2 page tables for the indirection, is we have to pay for a slightly larger hash table, but we can do a single hash table lookup to identify where the page is located, if it's located on DRAM, NVM, or SSD. So for the regular path, while all the data is in NVM at least, we do exactly the same thing. We do one page table lookup in case the page ID is not already swizzled. Okay, good. With this, I'm almost done and I'm almost concluding. But with the conclusion, I want to show the actual performance results of our system. And I hope you can kind of recognize our dream chart from the beginning in this. So we still have on the very top here the main memory system, which outperforms everything else. But then we have this blue line. The blue line is the 3-tiered buffer manager, our system, however. And what this one does is it's actually rather close to the main memory system. It then, when we hit non-volatile memory, we drop in performance, obviously. However, we can still leverage this DRAM cache to be better than the NVM direct system here, the black line. And once we hit SSDs, our system again drops in performance, obviously, but it is still able to run. Okay, so to sum up, what we did is we designed this NVM-aware buffer manager and used it to scale across all these different memory hierarchies. And I think one other really important point here is that we are not really setting out to build the fastest system ever designed. No, we are trying to build a system that works on all these different hierarchies and therefore is cost efficient by being able to cluster with the buffer manager the data in hot-cold partitions. Cold data on SSD, warm data on NVM, and hot data in DRAM. So yeah, that was our goal, and I think we mostly reached it. Thank you for your attention.
Right, we have plenty of time for questions.
Oh.
Hi, thank you for your talk. I was wondering, since you're showing all these impressive throughput numbers, but one of the key aspects of NVRAM is also latency, as you had on the first slide. If you also measure the latency that you're introducing through these buffer management techniques.
Oh, I think we haven't really looked at this. So you mean like a single transaction if the latency for that gets higher?
Exactly.
Okay, we haven't measured it, but I would assume it actually gets a little bit lower as long as we are still in DRAM, right? Because we can access it faster. However, yeah, if we hit NVM, we are probably slower than an NVM direct system, and we hit SSD, we are probably even slower than that.
Thank you.
Sure.
Hi, quick question. What happens if you go beyond that? So do you see any benefit if you have NVRAM in your system when the data grows larger?
When the data grows larger than the second line here, you mean?
I mean, if you go for large data. So do you see any benefit from NVRAM then?
Okay. So in this chart, we only show our system, right? So there's no other system. But we actually, we also did these experiments by comparing to a standard buffer manager, so that only uses DRAM and SSD. And we can see, at least at this point, I think it's still a factor of 4, which we are faster than a system that doesn't have this NVM cache. So the NVM cache actually pays out a lot here.
Okay, thanks.
One question, so you still seem to do write-ahead logging, is that correct?
Oh, I haven't mentioned it, but yeah, that is correct. But we haven't implemented recovery yet. This will be a follow-up work.
Okay, right, that would be a big benefit of the NVM direct alternatives, right? They could potentially avoid the complete recovery effort, right? Because you can just load the persistent data structure.
Yes, that's true, but so in this approach we're already writing redo and undo logs. So we have that, but we don't implement the recovery stuff. One problem that we can rather easily solve is with our write-ahead log, we can also do a replica on another system. When these NVM direct systems want to do that, they might also run into problems there.
Just last comment, the classification of how HANA uses NVM, I think we need to discuss it offline. I think it's not
Sure.
exactly correct.
Yeah, I might have oversimplified it a bit, sorry.
Hi. Did you make any observation on the performance of scans? I assume the transaction or index access.
Yes, we did. We also looked at scans. I don't have a slide for that. Scans, I can show you it's a poster if you have time.
Okay, perfect. Thank you.
Great.